Let's take a look at another really good question here. This one is, why does one can of soda sink and the other can of soda float? Well, let's look at this Diet Coke here. The Diet Coke must have a density that's less than 1 gram per milliliter, because we know that water is actually 1 gram per milliliter. And if something is floating, it's going to have a density of less than 1 gram per milliliter. So that would be the assignment we're going to give for that Diet Coke. For regular Coca-Cola, we know the density is going to have to be greater than 1 gram per milliliter. And we know that because it sank to the bottom. And we know that the water itself is going to be 1 gram per milliliter if it's pure water. So the Diet Coke is actually going to be more buoyant because the buoyancy force, which always points upward, in this case of the Diet Coke, will be greater than the gravitational force, which is pushing down on it. Notice how I drew the buoyant force arrow larger than the gravitational force arrow? And in the case of the classic Coke, the gravitational force, because of increased density and decreased buoyancy, will be greater, and as a result, the Coke sinks to the bottom. Now let's take a look at balloons and boats. In this case, it shows you a picture of a boat where it has an arrow that's going downward and of a certain size, and an arrow for buoyancy, which is going up of a certain size. And you see in the small writing there, it says the density of the boat and the density of the water. Now, if the density of, or if the gravity arrow on a test question is really large, and the buoyancy arrow is really small, whatever is in the middle is going to end up going down or sinking. In the case of this boat, the buoyancy arrow should actually be larger. This model doesn't exactly show that because the boat is floating. And the gravity arrow should definitely be smaller than the buoyancy arrow. That's why that boat is actually floating right there. And that means that that boat is actually positively buoyant. Let's look at the hot air balloons. You see, the more volume a hot air balloon has, the more lift it's going to have. Therefore, the more buoyant force it's going to have. Over here, with a smaller hot air balloon, that has less volume, it's going to have less lift. Now, if these balloons were to go up into some really, really cold air, and the little fire that was burning inside of here to heat the air inside the balloon suddenly went out, what do you suppose would happen to that balloon? Would it immediately fall from the sky? Probably not immediately. But the molecules of air, hot air inside the balloon, instead of rapidly bouncing around all over inside the balloon, they would end up contracting on each other a little bit more, becoming closer together. The balloon would lose its volume, and yes, the balloon would slowly start coming back to the ground and becoming negatively buoyant. So there are 3 different types of buoyancy. There's positive buoyancy, negative buoyancy, and neutral buoyancy. Take a look at the size of these arrows. Where it's positively buoyant, the buoyant force, which represents the upward arrow, is going to be larger than the gravity arrow, which is pointing down, which is going to be smaller. So you notice all of these arrows that are pointing upward, they all represent the buoyant force. In the case of hovering, which is going to be neutrally buoyant, the buoyancy arrow is equal to the size of the gravity arrow, which means that particular object, whatever it is going to stay in the same place and hover. For something that is negatively buoyant, you can see the buoyancy arrow is pretty small here, but the gravity arrow is significantly larger, and as a result of that, the object is going to sink. So now we've covered a little bit more about density and introduced the term for buoyancy.